Actually, this, are you able to see my screen? This is actually wrong. If the interpolation value which I took was wrong. This should have actually been 412. Okay, and with this value, what happens is I get this something close to how much is it? 1080 or something close to this I get. And obviously this will change. You can find whatever is appropriate. And this also changes a bit. So this becomes 0.8. Okay, this actually becomes 0.8, and something similar also you'll get here. You'll be able to get something similar close to this. Okay, so this is just one change because now when I had actually done this interpolation, instead of FE500, I had looked at this table and interpolated. That is wrong. I should have looked at FI500 table and interpolated. I would have got this. Okay, so that's a small minor error, which it's not minor, it's a bad error, but at least I know where I made the error. Okay, so only this change you make and you do the same procedure, you will get some different value for ASC and PC as well. Okay, so these things will get a different value. So okay, anyway, that's the one thing that I wanted to tell. And continuing with that one, if you remember here, we had actually usually we do this check, for control of deflection. Okay, generally we have this L by D should be lesser than or equal to 20. Okay, so for simply supported beam, so we have this. Now for doubly reinforced beam, we can make a modification to this number 20. Okay. Okay, so how do we make this modification? You open IS 456. So if you're able to see my IS 456 now, you can see this page. I'll maybe make it a little bit bigger. Okay. So you have two tables. One is modification factor for tension reinforcement, and another factor, modification factor for compression reinforcement. Okay. So you have this table, and here we need to first pick out some. So this table can be used. So not table, the figure. The figure for number 4. This can be used for both singly reinforced and doubly reinforced beams. But usually for singly reinforced beams, we give whatever area of steel we need and we just make a minor modification to it. So generally we do not bother about this modification if it is a singly reinforced beam. If it's doubly reinforced, we may want to have a look at it because area of cross section of steel required by that provided will be a bit different. Okay, especially in doubly reinforced beams. Okay, so when I do this thing, in fact, so what I will do is I'll just have a look at this whatever steel I have provided. I look at what steel was required and choose the appropriate value out of this table. Okay, so I'll just show it now. Okay, so for my problem which I have taken, so I will first calculate this value, Fs equal to 0.858 Fy into area of cross section steel required by area of cross section steel provided. Okay, so let me just find that out. So Fs equals 0.58 Fy. Okay, times the area of steel required. The area of steel required was 2240. Okay, yeah, shown here 2240 was required, and we provided 2277. Okay, so that is the ratio we take. So AST required by AST provided are 0.58 into 500 into 2240 by 2277. So find this value. Okay. How much do you get for this? Do it very quickly. 0.58 into 500 into 2240 by 2277. How much is this?
So 285.28.
285.28.
285.28.
Okay, 285.28 Newton per millimeter square. So we'll go back to this chart. Okay, let's look at where 285 may come. It is somewhere near this. To be very, if you want to make it very simple, you can just choose Fs equal to 290 or make a slight modification to it. The percentage of tension reinforcement, which is actually there, that is about 1. Let's have a look at the percentage. 1.68%. This is what we've actually given. 1.68% of steel. So 1.68% means probably somewhere over here. Okay. If I have a marker, let me just. So somewhere corresponding to this point over here. Let's see where that comes. Over here. So modification factor is about 0.75 or something. Okay, it comes to about 0.75. Okay, so we just say PT is 1.68%, and corresponding to that we get modification is about 0.75. So this is what the tension reinforcement we got. Okay, so I hope you understood it. But percentage of tension reinforcement which you have given and the Fs which you have calculated. Based on that, you can get a modification factor for tension reinforcement. Similarly, you can also get it for compression reinforcement. So how much percentage of compression reinforcement you have given? Okay, that thing. That as I told you, no, anyway, this was wrong. It will be about 0.8. It will be close to 0.8. Okay, when I make this correction, it actually becomes 0.8. So 0.8 is the percentage of compression reinforcement. And there's nothing else you need to look at. Just look at 0.8. It will be somewhere over here. Intersecting somewhere there, maybe 1.23 or something. Okay. So PC modification. For another 0.8% PC equals 1.23. So now what we'll do is we'll just modify and check our depth. So is my depth lesser than or equal to length was length what's like 7 meters? Okay. In the overall length is 7 meters times that's it, 7,000 divided by the, not multiplied by, sorry, divided by 20 into 0.75 into 1.23. So how much does this depth come? How much is this?
So 379.4.
Okay, 379.4 mm, and we anyway given 450 mm, so it's okay. So therefore, okay for deflection control. Okay, this is okay for deflection control. Of course, other than that, so there's a separate way of checking deflection. This is for control of deflection based on the depth of the beam. Okay, so this is one criteria. The other deflection criteria I'll tell you a bit later, maybe next class. So this is one thing, and the other thing that I wanted to tell you is, like how you did for simply supported beams, how do you use SP16 for this? It's very similar. Okay, very similar to that. So I'll go to the relevant section of SP16. Okay, so mainly you'll be using two things. One thing that you'll have to use is this table. Okay, table E. Okay, this table E is one thing that you will have to use to get a PT limit. Okay, why? Because if you look over here, what is the first thing that we find? We find the MU limit, and for this MU limit, we find out how much that corresponding steel we have to provide. Okay, so corresponding to this, we have to find. I'll close this. I don't need this anymore. So corresponding to that, the first thing we need to find is PT limit. Then we use. Then we come a bit down, and we will use this table. Okay, to find out what is the delta AST. AST2 over here refers to delta AST2 over here refers to delta AST, which we found in the problem, and ASC obviously means ASC. So using this we can find, and so one by one we'll do. So we have to use this table along with charts 19 and 20. Okay, so what are these charts 19 and 20? So I'll just go there. So this is chart 19. It is for flexure for doubly reinforced beam. As you can see, it is written over there. Flexure for doubly reinforced beam. What are the axes? It is D minus D dash and AST2. Within that you have graphs of MU2. MU2 means like your delta MU, which you found in the problem. The delta MU which you found in the problem, that corresponds to MU2 as shown over here. Only thing you should remember is this chart is only for Fy 250 Newton per mm square. It is not present for any other grade of steel. If you have any other grade of steel, you have to use the table, modification table, which I showed you just a little while ago, a few pages back in this. Okay, so this I'll tell you how to do. So for us in our problem, our delta MU is 169 MU, or in SP16 it is written as MU2. Okay, so that is 169 into 10 power 6. Okay, let me keep this 169 kilonewton meter itself. Kilonewton meter. Okay, my D by D dash by D, oh, sorry, not D dash by D, D minus D dash. D minus D dash is 450 minus 50, which is in 400 mm or 40 centimeters. I written in centimeters because in SP16 it is given in centimeters. Okay, so this is in centimeters, and I am looking at 169 kilonewton meter. So it is somewhere over here. Okay, 169 kilonewton somewhere over here, and I am looking at 40. So let me say maybe this 169 means approximately 170. So this is the point that I am looking at. And I see corresponding to this, what is the AST2 that you see corresponding to that point? I kept it midway between 160 and 180, which is close to 170. And I've kept it at 40 centimeters D minus D dash. So what do you see for AST2? Are you able to see my cursor being dragged? That blue color patch, are you able to see?
Yes, sir, 20
centimeters square. So that is our AST2 or delta AST. If it was 250 Newton per mm square, then it has to be 20 centimeters square, or in mm square it is 2000. But we have Fy equals 500, not 250. Okay, so for this what should we do? So we go back a few pages, and we have multiplying factors for use with charts 19 and 20. Okay, so we have to use these multiplying factors. For delta AST, my multiplying factor is 0.5, and the same multiplying factor for AC is my d by d dash is 0.11, so I can probably use this 0.54. Okay, so 0.5 for AST2 or delta AST, and 0.54 is the factor for ASC. So my AST delta, I'll make it as delta AST. Modification factor is 0.5 and ASC modification factor is 0.54. Okay, so 2000 times this is about 1000 mm square, and 0.54 times of this is about 0.54. Okay, this is about 1080. Okay, so this is the so we found delta AST and ASC. So remember that our total AST is nothing but AST limit plus delta AST. Okay, so remember this. This is what is our total AST. So the remaining thing which we do not have yet is AST limit. So AST limit. Okay, we can find easily. That also there's a table just a bit above. So we have a table over here for delta AST, FCK25 and FCK25 and FE500 is 0.94. Okay, so if you remember, you can see over here that you got the same 0.94 when you did it. So AST limit is 0.94 into 300 into 450 by 100, and you will get the same number. That was what is it? 1269. 1269 mm square. So how does this compare with what we already got previously? So delta ST we got 1000 from this. So previously, if you look, we got. Did you get anything close to it? Yeah, you got 971 instead of 1000. Okay, somewhat close. And similarly, as I told you, you will get ASC something close to 1080 when you make this correction to 500. And same thing you get when you go by this process as well. So this is using the charts. Sorry, using the charts, and that's a much simpler procedure itself. Okay, in SP16 using tables. This is much more simpler and smaller than this. And I'll very quickly go there. Yeah, so Flexure reinforcement percentages for doubly reinforced sections, FCK25, F500. For this particular grade of steel and concrete, the table number is 55. Different grades of steel and concrete will have a different table number. So here it's pretty easy. One thing you will notice is you see the starting number of ME by BD square. Okay, it is 3.33. The starting number of ME by BD square itself is 3.33 for F500 and FCK25. Now what you will observe is, if you go to the singly reinforced beams table, okay, so FCK25, if you look at this table for FCK25 and FE500, you see that the last number of ME by BD squared you have value still is only till 3.32. Okay, so only till 3.32 you have singly reinforced section table for FCK25 and F500. Okay, are you able to see this? So for this grade of steel and concrete, the singly reinforced section ME by BD square, it stops with this value. Okay, there are no values below ME by BD for ME by BD square greater than 3.32. There are no PT values given to you. Okay, meaning that it is not possible to have a singly reinforced section to be under reinforced or balanced if your ME by BD square is going to be greater than 3.32 for this grade of concrete and steel. So in such a situation, you will have to be doubly reinforced and go to that relevant table. That's why you see that it starts from the very next value of ME by BD square. Okay. So now for our problem, we see that our MU by BD square is 671 into 10 power 6, sorry, not 671, what am I writing? 371 rather. Okay. 300 into 450 square. Just get me this value alone, I'll finish the rest in a second. Of course, d dash by d is 50 by 450 equals 0.11. So how much is MU by BD square? Yeah, how much is it? How much is MU by BD square? Please, I want to finish the class in another 1 minute or 2. I'm asking you a very simple thing. I'm not asking you anything special. Just give me the result of this.
6.10.
6.10. Okay, fine. 6.10. Now let us go there. MU by BD square. Let us look at this column. Where is 6.10? 6.10 is here. Okay, this is where 6.10 is present. And we have our d dash by d as 0.11. So we have for 0.1 and 0.15. So we'll have to find something in between it. So for 0.1, PT is 1.653. For 0.15, it is 1.695. So if you carry out an interpolation between these two, you would get PT equal to something close to this. You will get PT equals 1.661%. Okay, if you make the interpolation between it. And similarly for PC, it's 0.797 for d dash by d 0.10, and for d dash by d 0.15 it is 0.88. And you carry out a similar interpolation, you get it's 0.770 for 0.1 d dash by d and 0.850 for d dash by d 0.15. So the interpolation between this will give you 0.7. 0.11 only or no 0.79. Okay, PC will come 79%, and according to this you can find out the AST and ASC. But mind you, this is the total AST, total PT rather. Okay, not limit delta AST, delta PT or nothing like that. It's the total one, which comes after adding delta AST and AST limit. That is this value. So if you compare it with what you got in the problem, you got 1.68. Here you got 1.66, slight difference. And suddenly you will get about 0.8 for PC. Here I'm getting slightly lower, 0.79. So these are much simpler, direct ways of doing the design of. So in the project, if you're doing, you can adopt this SP16 procedure. But if you're going to write an exam, then unless I say that use SP16 procedure, do not use SP16 procedure, do the full analytical procedure in the exam, unless I otherwise specify and tell you that use SP16. Okay, if I simply say design the beam and you do based only on SP16, I'll give you only a fraction of the marks. Okay, because I do not know whether you know the actual theoretical procedure behind it or not. Okay, so this is what I wanted to show you today, how to use SP16 for doubly reinforced beams. Okay, so with this I'll stop, and from Wednesday's class we'll continue with slabs and flanged sections. Okay, so I'll stop with this. Thank you. Meet you again on Wednesday. Okay. Right. So shall I leave? Do you want to ask anything? Thank you. Okay, fine. Vigneshwar, that boy in Lucknow, did he write or did not write?
He didn't write, it seems, sir. He didn't
Didn't
mention
write.
he wrote the exam.
Oh, he wrote.
No, sir, he didn't write.
Didn't write. Okay, fine. Let me see later. Fine. Okay, fine. Bye. We'll meet on Wednesday. Okay, I'm ending the meeting. Bye.